type your questions there, and we'll get to them at the end. So this briefing is about astronomy from the very largest to the very smallest scales, although actually we're going in the other order, from the very smallest to the very largest scales. We have 3 speakers. The first will be Chris Arumainayagam from Wellesley College in Massachusetts. He'll be speaking on low-energy electrons in astrochemistry, a tale of 2 molecules. Then we'll get really big, really fast. We'll hear from Philip Hopkins at Caltech, his talk entitled Failures No More, the Radical Consequences of Realistic Stellar Feedback. And he'll be talking about scales from stellar to galactic. And then finally, Gregory Walth from University of California, San Diego, right here, will be speaking on using cosmic telescopes to study dusty star-forming galaxies. So again, we'll hear from each of them in succession, and then we'll take your questions at the end. So I will turn it over to Chris. Did I do okay with your name?
Very well. Excellent. First of all, I would like to thank Rick Fienberg for giving me this opportunity to speak here. The title of my presentation is The Role of Low-Energy Electrons in Astrochemistry.
Chris, I need you to face this so that you're...
Okay. I'm a faculty member in the chemistry department at Wellesley College. Wellesley College, as you may know, is a small liberal arts college about 16 miles west of Boston. All of the research that I will be talking about was done at Wellesley College by undergraduate students. The speaker for tomorrow's conference presentation is Jyoti Campbell, who is a sophomore at Wellesley College. So since the dawn of humanity, we have always wondered, how did life originate on Earth? Broadly speaking, there are 2 theories. One is an endogenous theory, and the other is an exogenous theory of life origin. The exogenous theory of life origin is what causes people to say that we are stardust. So in this diagram, I would like to explain to you this theory in a very simplistic manner. If we start at the extreme left, the diffuse molecular clouds, when the gravity becomes insurmountable, that diffuse cloud becomes a dense, dark molecular cloud. Even though we call it dense, the pressure in these clouds is about 10 trillion times less than the pressure of the atmosphere here on Earth. And it is in this region that most of the interstellar molecules are synthesized. So you can think of this as the chemical factory for the synthesis of complex organic molecules. Then these dense molecular clouds, under further gravitational pressure, form an accretion disk. And this accretion disk is the precursor to the stellar system, which you might think which is actually the solar system, the solar system is an example of the stellar system. And it is these comets in these stellar systems that are thought to bring prebiotic molecules to planets, whether they be Earth or exoplanets. Just last month, unambiguous evidence for the presence of glycine was found on a comet. Then, when the star ages, it explodes as a supernova, and the whole cycle begins over again. So what we are trying to do is to do a little bit of chemistry that mimics what goes on in the heavens. Over 200 different molecules have now been identified in the interstellar medium. Here is a partial list of these molecules. Molecules as complex as fullerenes have also been identified. So the question is, how were these molecules synthesized in the interstellar medium? The widely accepted hypothesis for this synthesis is that there are ice mantles surrounding dust grains inside these dark, dense molecular clouds, and the UV photons incident on these ice mantles produces complex organics. So let me explain that with a few animations. So what we have is a carbonaceous dust grain, which is shown in black and white. And on top of that is a thin ice layer, which is about 100 molecules thick. The size of the dust grain is about 0.1 microns. But because this is in the dark, dense molecular clouds, it's surrounded by hydrogen molecules. So if you think about a molecule such as methanol, which is a cousin of ethanol, which is part of every alcoholic drink, this methanol molecule, when it interacts with UV light, undergoes an excitation, so the energy level of the molecule rises, and because of that, it can fragment and form these radical species. But this is all happening at 10 Kelvin, which means that the radical species cannot move around. They're frozen inside the ices. But if you have a cosmic ray particle incident on the ices will warm up, and these molecules will begin to move around, and they find each other and form a new molecule, ethylene glycol, which is the main ingredient of antifreeze in your car. So this diagram here illustrates the whole process by which interstellar molecules are synthesized in the dark, dense molecular clouds. UV light interacts with a molecule, causes the molecule to fragment, and those fragments then come together when the temperature rises. This is pretty much what everybody believes happens when UV light interacts with interstellar ices. Our hypothesis is a little bit different. What we are claiming is that low energy electrons could also play a very important role in the synthesis of prebiotic molecules that were previously thought to form only through UV photolysis. And we have done a set of systematic studies to verify this hypothesis. So in our thinking, what happens is that when cosmic rays interact with ices, These cosmic rays have energies on the order of 10 to the power 7 to 10 to the power 20 electron volts. When the cosmic rays interact with ices, they produce huge quantities of very, very low energy electrons. These electrons have energies on the order of 0 to 20 electron volts. And to give you a perspective, the typical bond dissociation energy for a bond is about 4 to 5 electron volts. So what we're claiming is that the low energy electrons produced by these cosmic rays are initiating chemical reactions which yield some of the products that have been identified in the interstellar medium. So here again is methanol. Now low energy electrons interact with the methanol, cause an excitation. The excited molecule fragments, and these fragments come together and form ethylene glycol. So you might say that electrons and photons produce the same reaction products, and in fact we have shown that about 14 of the reaction products previously identified by UV photolysis of methanol are also produced by electron-induced radiolysis of methanol. But there is one molecule, the molecule that is circled in this slide. This molecule is methoxymethanol. That molecule has never been observed in the UV photolysis of methanol ices. So what we are suggesting is that finding this molecule in the dark, dense molecular clouds may help us understand the relative importance of low energy electrons compared to UV photons in initiating these chemical reactions. So let me conclude by saying that what we have found is that low energy electron induced reaction could account for most of the molecules that have been found by UV photolysis under similar conditions. And finally, molecules such as methoxymethanol may serve as tracer molecules for the difference between photon and electron-induced reactions. I'd like to end by acknowledging our collaborators and the students working in my lab. Dr. Michael Boyer at Clark University, Dr. Leon Sanch, Dr. Andrew Bass at the University of Sherbrooke, and Dr. Petra Swedrick at the University of Bremen. At the end of this past semester, I had 21 students working in my lab, and those names of those students are shown in the bottom right-hand corner of the slide. Thank you for your attention. And now it's going to be Phil who's going to take over.
All right. Well, now we're going to, as Rick said, dramatically jump upwards in scales. And for me, I'm going to start using phrases that imply that stars are small things, because for me, the big things are what you're seeing here, the galaxies. So these are all simulations from the project I'm going to be telling you about, the FIRE, which stands for Feedback in Realistic Environments Project, and specifically Andrew Wetzel, a postdoc at Caltech, who's going to start as faculty at UC Davis in the fall, has led a lot of the work that I'm going to be telling you about. So the big picture, of course, if we want to understand galaxies, is how we go from the Big Bang to the Milky Way. We have some idea, we think, about the initial conditions of the universe, and the ingredients that make up the universe, but we don't understand how we get these beautifully regular galaxies that we see today, like the Milky Way, like these beautiful disks, etc. And I could give you an hour-long talk about all the problems that we've historically been unable to solve in galaxy formation, but in 1 minute, just one example is shown here. This is the famous missing satellites problem, and the issue is that if you take a naive calculation of gravity with dark matter and assume that the dark matter clumps that have collapsed under gravity should drag the normal matter with them, you predict that a galaxy like the Milky Way should be surrounded by millions of tiny satellite substructures, which is what's shown on the left. And we observe maybe a couple dozen that are in the ballpark of what we might call these kinds of massive substructures. So where are these missing satellites? A related problem that people have started calling the too big to fail problem in cosmology is that, okay, maybe I just say these are there, but they're all dark. They just don't have stars in them for whatever reason. They didn't form stars. They're invisible. Okay, that might get me out of some of this problem, but then I can just say observationally, well, the couple dozen I see should presumably be the biggest ones. Those would have the most stuff, so they'd be the easiest to see. So I'll just measure their masses directly and compare them to the masses of the biggest things you predict in your dark matter simulation. And the masses that I infer from the observed satellites are much too small compared to what my theoretical naive prediction is. So hence too big to fail. Now what these models miss is, of course, that galaxies don't just form stars and sit there. Stars are not passive, they're very active. So the animation here is showing you a supernova explosion, which of course we know happens all the time, and when one of these supernovae explodes, it injects a tremendous amount of energy. And in fact, if you integrate up all the energy that supernovae have emitted over the course of a galaxy's lifetime, it's greater than the gravitational energy holding the galaxy together. So you cannot ignore it. And we see an example of that in life in this big image of the galaxy M82. You're looking at X-ray emitting gas that's being launched out from the galaxy, out to many times the size of the galaxy, at hundreds of kilometers a second, by a bunch of supernova explosions occurring in rapid succession in the center of the galaxy. So what we've been trying to do with this FIRE project is incorporate these physics into the next generation of models of galaxy formation and really push the simulations forward. And this is showing you a comparison of the previous state of the art a few years ago. This is one of my simulations, so I'm picking on myself here. And you can see it forms a sort of spirally structure, but there's nothing happening inside the galaxy. And that's because we didn't have the physics or the resolving power to actually properly do all the things that are happening inside the galaxy. On the right, you've got the next generation of simulations. This is now following the dense phases of gas that collapse and form individual stars inside the galaxy in molecular clouds. And then those stars form, they start radiating the medium around them and photoionize it and warm it up to the sort of pink gas you see until they explode as supernova, heating gas up to millions of degrees, the yellow material you see that vents and explodes out of the entire galaxy, launching into the intergalactic medium. And what Andrew has been doing is really pushing the frontier on these simulations. So this is a plot of the mass resolution, basically what are the smallest structures that we believe in terms of their mass relative to the mass of the sun in the simulations, and the spatial resolution, the size scale in parsecs that we get down to in these simulations of a single galaxy of about the Milky Way size. And what I've plotted here are the last sort of 10 years of history of this field by our group and many competitor groups. The first wave of these FIRE simulations lives about in the middle of this plot, where you can see here Andrew's newest latte simulations. Latte is derived from the Milky Way on fire. You got to have pun names if you want NSF funding these days. And we've just started running triple latte, which really crushes the record in this field by a factor of 100 higher resolution than has ever been done before. And we're not just doing this for bragging rights, we're doing it because there's fundamentally new physics that you start to be able to do when you have this kind of resolution, treating things like individual supernova explosions and really adding up how they affect a galaxy, as well as resolving these tiny substructures that I began my talk by saying they live around the Milky Way and we don't understand where they should or shouldn't be. So this is what it looks like in a big simulation. We throw this all in the cookpot. This is one of these simulations showing how the stars and gas evolve over cosmic time. The stars are sort of a mock Hubble image, if we could see with perfect eyes at all redshifts. and this is the redshift counting down from the early universe to today in a box about the size of the dark matter halo that will enclose the galaxy today. And you can see on the right the incredible violence of this galaxy's formation. As these stars form very rapidly in the early universe, they also live briefly and explode and die violently, ejecting material far from the galaxy, suppressing galaxy formation, but also stirring everything around. They're not just getting rid of gas, they're really dynamically, violently perturbing the entire system. So it's not a sort of smooth, quiescent formation of galaxies. And it's not until quite late times, around, you'll finally see it start to happen after one last gasp and explosion, that it settles down and starts to form what we would call a recognizable galaxy today, sort of a nice disk of gas and stars. And if you actually run this all the way to today, here are some of the galaxies that you get out. And I like showing this at conferences now in the last few weeks and trying to trick observers into guessing which ones are simulated and which ones are real galaxies. And some of them can still do it, but some of them I'm starting to actually be able to trick people, which is a big victory in this field. But what about quantitative comparisons? So let's come back to the structure of these galaxies. Well, there's many ways we could compare them, but I said that these big galaxies that we observe around our own Milky Way, they're just not as massive as you would predict naively from the theory. So this blue line shows the naive prediction from the old simulations, where you put in the gravity and the chemistry and you assume the dense gas turns into stars, for how dense the dark matter is as you go in towards the center of each of these individual dwarf galaxies. The stars are roughly what we observe. It's not as dense, the dark matter. And this is the result of these new simulations. If you want the quantitative details, you can see the papers that are referenced here. But what the movie is showing you is just how this galaxy is violently churning through all of its time. And that's kicking around the dark matter as well as the normal matter. So it's really just that dark matter is being ejected because it's being gravitationally pulled by all these bits of gas and normal matter that's being thrown around by the supernova explosions. And you end up with these ridiculously fluffy galaxies that we were actually starting to worry were fluffier than anything we'd ever observed until people like Aaron Romanowski and Peter Van Dokkum started telling us in the last year that they're discovering new classes of ultra-fluffy galaxies. On the left, you see one of those, and on the right, you see one of these simulated dwarfs around the Milky Way in these ultra-high resolution simulations. And those are individual stars, each of those little pixels that you're looking at there. And just to come back to conclude, let's look at this structure problem of the missing satellites around the Milky Way. So on the left, you have the prediction if we just had dark matter. On the right, and it may be a little hard to see on some projectors, but you can see that there's far fewer of these little bright white spots. These are the substructures that would be there in a model where you only have dark matter on the left. But really, when you go to the far right, when you look at the stars, you see that they're totally absent, basically. So they're both being destroyed by this violence and by just material being ejected and therefore never being able to form stars. And we can zoom in to this galaxy and look at the sort of Milky Way that forms at its center. And again, we're starting to actually have galaxies that don't look crazy, which if I gave this talk 10 years ago, you'd think I was crazy for saying that. But it's an exciting time to be doing these comparisons today. Thank you. All right, and with that, I'll introduce Greg.
Thank you. Today what I'm going to talk about are how we use cosmic telescopes to investigate dusty star-forming galaxies. And in this one particular case, a giant luminous star-forming region at intermediate redshift. So at redshift 2, we've discovered that essentially star formation appears to be clumpy. This clumpy form of star formation it appears in these giant star-forming regions, which you detect in H-alpha. Here in this Ginzel et al. Paper, you can see that essentially the clumps are just kind of erratic. They're all over the place. And it's not even exactly clear how these galaxies are forming. Some of the formation is through mergers. Other formations are through in situ, or where the galaxies are forming in isolation. And the thought is generally that the gas fractions in these galaxies are so incredibly high that that's essentially what causes these clumps to form. They're very unstable gravitationally, and gravitationally, because of that instability, the clumps form very quickly. Now, if we kind of fast forward to, in the local universe, we see that these type of galaxies don't really exist. Essentially, kind of a good local analog of what is common in the local universe is essentially just mergers of these giant galaxies that form these giant star-forming regions. So essentially, the star-forming regions that form locally are through some sort of merger action, whereas the galaxies at high redshift, it's either they're forming because they're forming just in isolation, or they're forming from mergers. But what makes it spectacular at higher redshift is the fact that the star formation rate at redshift 2 is many-fold higher than what you see locally. And it sort of begs the question of what is the physical conditions of these galaxies at redshift 2 compared to what we see in local galaxies. And some of the suggestions are that gas fraction is one element, temperature and density is another element, and the basic formation properties could be potentially different at these higher redshifts. So what I'm going to talk about is a galaxy that we found at intermediate redshift that exhibits properties much like a galaxy at redshift 2, but has properties also like a local galaxy as well. Here in this image, this is one of the Hubble frontier fields. This is Abel 1063. It's at redshift 0.35. Essentially what we're doing is we're using this massive galaxy cluster to act as a giant cosmic lens in order to probe the background galaxies. The zoomed in region is one of the galaxies in question that we're studying, and as you notice, there's a bright clump on the edge of it. This particular clump is a giant star-forming region, kiloparsec in size and forming stars at about 10 solar masses per year. If you look at the bottom panel, this bottom panel essentially shows, from our information of the mass model of this galaxy cluster, what it would look like reconstructed. So for this galaxy in particular, it's actually much further outside of the high magnification areas of the lens, so the models that constrain it are much more reliable. So you see something like a factor of 4 to 5 in the magnification, in the amplification of its flux, and also in the linear stretching that you see. And you can see that in the lens model reconstruction, where we take this model and try to determine what it looks like behind the galaxy without the lens in the way. And you can see it just looks like it's essentially stretched. This stretching is actually very useful because it allows us to probe to very high spatial resolutions. In this particular case, up to 200 parsecs in resolution. So essentially, we can determine that this is a single clump, at least up to 200 parsecs in size. But as you can see, it's obviously a kiloparsec, and the fact that you would have to have like 5 of these things lined up in a row would be a very unusual chance in the universe. What is striking about this particular galaxy is when you compare it to other galaxies that are known, essentially this plot is showing the star formation rate of individual star-forming clumps in galaxies compared to the size of these individual clumps. The gray points represent galaxies that are at redshift 0, or very local galaxies, and you can see that their sizes span a range from tens of parsecs to a couple hundred parsecs, but their star formation rates are only like fractions of a single solar mass per year. They're very, very tiny star formation rates. The blue points represent all redshift galaxies that are star-forming clumps that are at redshifts greater than 1. And as you can see, there's some sort of scaling up that's occurring, sort of like what I was alluding to in the background, is essentially that these clumps are, not only are they larger, but they're actually more luminous. And the striking point to really sort of take away from this particular galaxy is, even though it's at intermediate redshift, at redshift 0.6, it has a star formation rate, the clump has a star formation rate and its size that's as large as these galaxies in the upper size band and luminosity band. This is pretty shocking and also very fascinating. This sort of suggests that essentially these giant star-forming clumps are not just limited to galaxies above redshift 1, that may be perhaps that they're actually at much lower redshifts. It's been suggested that essentially as gas fraction of these galaxies, the content of gas decreases as you go to lower redshifts, essentially this kind of drives some sort of evolution. This is maybe like one of the first examples. This may not be the case. Of course, how do you form these giant clumps? This is something that's really kind of something fundamental that we want to try to understand. How do these giant clumps form? And if they're forming at high redshift, we think we have a good understanding, but if they're forming at low redshift, it may be actually a little harder. And of course, this just may be a rare object. It may be just one of millions or billions that may be out there that just aren't. It's just a very extremely rare object. So anyway, I'll go ahead and conclude basically saying that we've discovered this giant star-forming clump at redshift 0.6. It's about a kiloparsec in diameter. It has a star formation rate of 10 solar masses per year. This is very comparable to what you see at redshift 2, but it's, as far as we can tell, very unusual to what we see at lower redshift. And this may be just because of the gravitational lensing that we're being able to resolve regions that you would be typically unresolved at HST resolution at that redshift range. And then in addition, this H2 region seems to have formed in isolation. It doesn't seem to form through some sort of merger event. And with that, I'll go ahead and end. Thank you.
All right, thanks very much. Let's go to questions from here in the room. First, let me see if we have any. Do we have? Good, okay. If you can come up, there's a microphone here in the chair. Wait for the microphone and identify yourself with your name and affiliation, and please indicate who it is that you're asking your question of. So it's right here, the second chair. Just flip the switch to on. Thanks.
For the first speaker, my name is Nola Red. I'm a freelance science writer. For our first speaker, I wanted to ask you why we haven't seen methoxymethanol. Is it observational, or we're just not looking for it?
I think it's a very difficult molecule to look for because a lot of the characteristic spectral lines are going to overlap with methanol, but nobody has identified this molecule in the terrestrial experiments, so nobody has looked for this molecule. So my hope is that someone will soon start to look for signatures of this molecule. It's a very labile species, which means that it decomposes very easily. In fact, you cannot get a bottle of methoxymethanol. It simply doesn't exist. You would have to go to temperatures on the order of 90 Kelvin to be able to isolate this molecule.
Okay. Chris.
Hi, it's Chris Crockett from Science News. Question for Philip Hopkins. I know that AGN feedback is often invoked to understand star formation history of galaxies and such. Can you comment at all about how the interplay between what you're seeing in your simulations of the supernova energy injection, how that interplays with AGN, and how those all work together to explain what we see?
Absolutely. So it's an excellent question. The truth is that we've only just started to really get into the AGN side. It's something I worked on before, but we've spent a while just focusing on the stellar side because the feeling is, at least there, we think we understand at least sort of how stars evolve. It's a lot more mysteries surrounding the supermassive black holes. But what we can see very clearly, so what I didn't show you is where these models clearly fail is you start going to masses above the Milky Way's mass, and it's clear that supernovae aren't enough. And many people have suggested this, so we weren't shocked to see that, but that's where we think it's clear that, and we've thrown all the stellar processes that we know exist sort of into this, and it's clear, I think, that that's just not enough to regulate sort of runaway growth of these galaxies. If anything, actually, it turns out the supernova make life harder because you're ejecting all this material, which means you're polluting sort of circumgalactic and intergalactic medium with a lot of heavy elements around these galaxies. And that stuff doesn't get lost forever, especially if you're forming like a massive galaxy cluster. It goes out and then gets trapped and brought back in. And when you pollute that medium with all these heavy elements, it radiatively loses energy much faster than it would have otherwise, basically. So it all just wants to fall on the final galaxy that much faster. So you're kind of, you're putting off the problem in a bit for the future, and you know, something kicks in eventually and saves the day, and we think that's AGN, but we don't have a simulation that does it yet.
Okay, any other questions from here in the room? All right, we have one coming in online. This comes from Camille Carlisle at Sky and Telescope magazine, and it's also for Phil. She says, so Phil, you basically have solved the missing satellite problem and the too big to fail problem. Do you have any predictions for how many satellites in total might turn up around the Milky Way? And what do the folks working with the Dark Energy Survey and other similar surveys think of those predictions?
So Andrew Wetzel, who I said is leading this project, is there's some preliminary predictions in the paper he just put out, but he's working actually on making a much more detailed sort of tool. What he really wants to do, because the detection of these super faint galaxies is so challenging, because there are 1,000 stars spread over a huge part of the sky, it's a little unfair to compare our theorists' box where we can just kind of look at it from any point of view and grab these galaxies to the observations when you really want to test the models. So actually what he's doing now is building a tool for exactly this purpose that'll be built with a front end that's exactly mirroring what's done in DES, and there's a Gaia front end as well, so that you can go in, give it your selection, and pull out exactly the satellites that survey should see. So I don't know what the answer will be yet. I'm hoping there's something that breaks down so that we can figure out something new, because there's a lot of potentially exciting things that could be lurking around the corner here.
Okay, good. Any other questions? I actually had one for you, Greg. When you were showing us the image of the galaxy in the frontier field with the bright clump, I got a little confused as to whether I was looking at a clump in that galaxy, or if I was looking at something that was lensed that was behind that galaxy. Can you just clarify that?
Yeah, no problem. So essentially in that image, what you're seeing, the reconstruction sort of helps us the best, but essentially what you see is a galaxy that has two spiral arms, and then embedded within one of the spiral arms, you see this star-forming clump. And the reason why we know the star-forming clump is actually within the galaxy is we've confirmed the redshift of the clump and also the galaxy together.
Okay.
We have kinematic measurements of the galaxy, which shows that the clump is actually rotating smoothly with the galaxy, so it doesn't appear to have any evidence for interaction.
Okay. All right. Well, if there are no further questions, we'll wrap it up. I'd like to thank our speakers again for presenting these results to us today. Our next briefing will be tomorrow morning at 10:15 a.m. It'll be on shaking hands and erupting variable stars. And I wanted to just remind the journalists who are here that I need to know by the end of the day today whether you're planning to come to Palomar Observatory with us on Thursday. Okay? Thank you very much. See you tomorrow.
Thank you.
Thank you.
All right. Did I get...